Bismillahirrahmanirrahim. Assalamu alaikum, dear students. I'm Arif and I welcome you all in today's session. To access the notebook for today's session, you can access course page on my personal website, arifpad.me. The other way is to download all the notebook files from course GitHub account, RFPUCIT, and all the notebooks for this course are housed in this public data science repository. Well, this is the Jupyter Notebook dashboard running locally on my machine at port 8888. And here is the notebook for lecture number 6.16 of the 6th module, Machine Learning, for the course titled Tools and Techniques for Data Science. Well, in today's session, I will answer the what, why, and how questions in relation to building machine learning pipelines. That is, by the end of today's session, you will have a crystal clear understanding of what do we mean by a machine learning pipeline, why do we need to build it, and how to create it using Scikit-learn pipeline module. Let's move ahead and see the sequence of today's lecture agenda. Well, my dear friends, today's session is going to use all the knowledge that we have gained in the last 15 sessions. For that reason, I will start with a quick but abstract level recap of all the tasks that we need to perform under the umbrella of data pre-processing and feature engineering. Example 1 will be a hands-on practice of applying different Sklearn transformer classes on a dataset to make it ready to be fed to a machine learning model. This example 2 will be an extension of example 1, where I will be using Sklearn's ColumnTransformer class that is used to apply different transformers on different columns of a dataset in a more simple and a very elegant way. We have covered this in one of the previous session as well. Well, after the setting the stage right, we will talk about the actual agenda, and that is what is machine learning pipeline, why to create a machine learning pipeline, and how to create a machine learning pipeline. After understanding the theoretical concept, we will create pipelined models using two datasets as shown in this image, which might look Greek to many of you, but don't worry about it. By the end of today's session, you will have a very crystal clear understanding of how these pipelines have been designed. So we have a lot to learn today. So let's start playing. My dear students, before proceeding any further, let me spend 10 to 15 minutes and give you a quick but informative recap on different data pre-processing techniques and scikit-learn transformer classes that we covered in our video sessions from 6.7 to I think 6.11. If you already know about these transformers or are interested only in studying pipeline, you can click the timeline below to jump to that part. Anyways, I personally strongly recommend to watch this quick recap so that you can understand the concepts in a better fashion later on. Well, generally speaking, data pre-processing are the tasks we need to perform on the dataset in order to make it ready to be fed to the machine learning model. And let me name the 6 tasks that we normally perform while pre-processing. They are detecting and handling outliers, missing values imputation, encoding categorical features, feature scaling, extracting information, and combining information. Well, let me click this link to visit Scikit-learn documentation page containing information about Scikit-learn transformer classes, which are used for different data pre-processing and feature engineering tasks like imputation of missing values, encoding categorical features, data scaling, and so on. Well, my dear friends, these transformers are actually Python objects that have fit and transform methods. Unlike estimators or machine learning models having the fit and the predict methods. Well, in today's session, we will learn to combine these transformers to make data pipelines. Please make time to go through these pages after this video session, and let me fall back to the notebook and talk about some of the basic transformer classes. Okay, first of all, missing values imputation. For imputing missing values in our dataset, we have two options. The first is univariate, which imputes values under a column by using the non-missing values under that column. And the other one is multivariate, which uses the entire dataset to estimate the missing value. Well, my dear students, for univariate, we can use Panda's fill-NA method or Sklearn simple imputer transformer. And while for multivariate imputation, we can use Sklearn iterative or KNN imputer transformer. And this we have covered in detail in lecture number 6.8. Interested student can watch. Let me move ahead. My dear students, by now we all know that most machine learning algorithms cannot handle categorical variables. So we need to encode them, which is a process of converting categorical values into numerical values so that they can be fed to a machine learning model. The three most common Sklearn transformer classes used for this task are one-hot encoder, ordinal encoder, and label encoder. Well, to encode nominal data having no intrinsic order like gender and city, we use this one-hot encoder. And to encode ordinal data like passenger class, shirt size, we use this ordinal encoder. Moreover, this ordinal encoder is used for encoding input features, while this label encoder, which is quite similar to the ordinal encoder, but this label encoder is used for encoding output labels. Hope this makes sense. Once again, for details on this topic, you can watch video lecture number 6.9. Okay, my dear students, the next pre-processing task we need to perform in most cases is feature scaling. Mostly our dataset contains columns having different units. For example, a person's weight might be stored in kilograms while the weight of gold might be in grams. And a machine learning model might consider a value of 300 grams to be greater than 5 kilogram and therefore can give us unpredictable results. To handle this issue, Sklearn provide different transformer classes again, like max-app scaler, min-max scaler, robust scaler, and standard scaler. The most commonly used is this standard scaler, which performs standardization of data. That is, rescale the data so that its mean becomes 0 and standard deviation 1. We should use this standard scaler when the data under the column is normally distributed. And if the data is not normally distributed, you should use a min-max scaler or robust scaler, which will rescale the values between 0 and 1. And this is also described over here in these tables. Once again, interested students who wants to go to the details of these concepts can watch lecture number 6.10 for details. Let me move ahead. Okay, outliers are a bit more tricky because they can be due to a mistake during data collection phase, in which case they must be detected and removed. On the contrary, if your machine learning model is going to detect anomalies in a banking transaction, for example, then you must not remove the outliers because this is what the model will be looking for later. Moreover, all the distance-based machine learning algorithms like linear and logistic regression, KNN and support vector machine are sensitive to outliers. However, outliers do not have much impact on tree-based algorithms like decision trees and random forest. So to handle the outliers, we first need to identify them, and this can be done using a univariate or multivariate analysis. Well, for a univariate, if the data under the column is normally distributed, anything below mean minus 3 times the standard deviation or above mean plus 3 times the standard deviation can be considered as an outlier. And this is also called the z-score method. And if the data under the column is skewed, we should use the IQR method. And any value below the first quartile minus 1.5 times IQR or third quartile plus 1.5 times IQR can be considered as an outlier. And for multivariate, you can use a scatter chart and depth based or distance based or maybe density based methods to detect outliers. Anyways, once these outliers are detected, the next step is to deal with them. And the three commonly used techniques to handle outliers are trimming, capping, and discretization. Once again, interested students can watch lecture 6.7 for details. So far, so good. My dear students, after this theoretical recap, let me give you a practical recap of using these Sklearn transformers on a dataset for crystal clear understanding of the pre-processing task. Let me load a sample dataset from a CSV file to a pandas data frame. Well, this dataset has 4 columns and 100 observations or rows. The 3 input features are the gender, CGPA, and IQ of a graduated student. The output column is salary in thousands of rupees. So this seems to be a regression problem. My dear students, the first thing we do when we are given a dataset is we explore the data, perform EDA on it, go through individual variables, carry out required pre-processing tasks, and make the data ready to be fed to the machine learning model. Let's check out the generic information about this dataset using the info method of the data frame. Let me say df.info. Good. So this shows that we have we have 10 missing values under the CGPA column, whose data type is float, and the gender and IQ of course has data type of object, and this salary, which is the output feature, is an integer column. We can also check out this using the isNull method of the data frame. Let me do that as well. df.isNull, and let me call sum on it. Okay, so we have the null value only under the CGPA column. Great. The data type of gender and IQ is object or string. Let's move up and see this data. Well, this gender column has nominal data having values male and female. So we can use one hot encoder on this gender column to convert it to numeric values, a vector of zeros and ones. Similarly, this IQ column is of ordinal data type having values low, medium, and high. So we can use ordinal encoder on this IQ column to convert these values to 0, 1, and 2 respectively. My dear students, at times there might exist many different categorical values which might not be visible from this tabular view of the data frame. For that, you can always call the unique method on that column. Let me do that as well. Let me call unique on the gender column dot unique, and you see the unique values. We have 2 unique values under this column, and let me repeat this for the IQ column as well. And you see we have 3 values: low, medium, and high. Great. Let's move ahead. Let's do a train test split on the input feature X and output label Y. Do note that I have intentionally kept the shuffle argument to false so that I can show you the mapping between these rows before and after the transformation is done. Let me just execute. So this is just the head of the X train. I hope this makes sense. Let us first impute the missing values under the age column. And for this, I have created an instance of a simple imputer transformer with a strategy of mean, since it is numeric. Then I have called a fit method on CGPA column of this X train, CGPA column of X train, and transform, of course, on both. I've called transform on the X train as well as on the X test. And of course, these have returned a numpy array which is being assigned to the CGPA column of the data frame. Let me write down CGPA over here. Let me execute. Okay, fine. You see over here we have a NaN value at the third row under the CGPA column. And over here you see it is imputed now. This 2.8845 is the mean of this column. So all the missing values under the CGPA has been imputed by this mean value. Great job done. We can also verify this using the isNull method. Let me do that. X underscore train dot isNull, and let me call sum on this, and you see now the CGPA column has no more null values. Great job done. Well, let's move ahead. My dear students, now we need to encode the nominal variable, that is a gender. I'm using a one hot encoder which will create dummy variables or one hot vector. And since the gender column has just two unique values, so by default it will add two dummy columns. But to handle the issue of multicollinearity, I have used drop is equal to first argument, so it will drop the first column. Let me simply execute the code. Great. You can see the values. Male has been replaced by 1 and female by 0. So you see male, female, male, female, female, male, female. This mapping is same. My dear, actually these there were two columns. For male it was 0, 1, and for female it was 1, 0. But after dropping the first column, we get a single column, 1 for male and 0 for female. I hope this makes sense. So we are left with the IQ column now. And on the IQ column, once again, I'm using the ordinal encoder. And while creating the instance, I have passed a list of unique values to the categories argument. Note the order: low, medium, and high, which will be assigned integer values 0, 1, and 2 respectively. Rest of the code is almost same as above. Let me just execute it. Great. If we move up and we see the first row is medium, then we are high. So medium is 1, high is 2. At row 3 we have a 0 under IQ, so 0 is low. I hope this mapping makes sense to you all. Now I think the data is ready to be fed to the machine learning model. So to keep things simple, let me use linear regression. So this is the model. This cell is going to create the model as well as call fit by passing the X train and Y train. So we have a trained model now. My dear students, if you evaluate this model, this might give you not much good results, as I have created this data set with random values and it might not even satisfy the linearity and independence assumptions, which are a must to apply linear regression model. Anyways, we wanted to learn to apply different transformers to our dataset and make it ready to be fed to the machine learning model for training. And I think we have successfully done that. Okay. My dear friends, once we are satisfied with the performance of our model, we deploy it in a server environment. The end users will then access it via some API or some web application having a user interface. And the user has to enter three values. Gender being male or female, CGPA a float value from 0 to 4, and IQ being a string, low, medium, or high. Now, once again, someone has to pre-process this input to make it ready to be fed to the machine learning model. My dear students, this we will of course cover in our next session, that is the deploying of the machine learning model. But for the time being, I have just manually converted this or transformed the input. Do keep in mind that these values should be in exact same sequence as expected by the model. That is, the gender should come first, then the CGPA, and then the IQ. Moreover, it has to be a matrix. So I have called this reshape method to convert this 1D array to a 2D array having 1 row and 3 columns. Let me just execute. Great. So we have passed this transformed input to this predict method, and the predicted salary for a male having a CGPA of 3.5 and having high IQ is 73.127 thousand rupees. My dear students, once again, this prediction might not be that accurate because of the garbage data on which the model is trained. Sorry for that. Let me move ahead. I think in some previous session we have talked about basics about the column transformer classes as well. However, before using the pipeline, let me give you a quick recap of column transformer. And let me click this link, Scikit-learn's documentation link of column transformer, which allows us to apply different transformers on different columns of our dataset in almost a single line of code. The two parameters of our interest are transformers and this remainder. Well, to the transformers argument, we need to pass a list of 3 valued tuples containing a unique name, transformer class instance, and a list of columns to which you want to apply that transformation. Well, the second argument is this remainder, which has a default value of drop. So by default, a column transformer returns only the columns on which it has performed a transformation. If you want the remaining columns as well to be returned, you specify remainder is equal to pass through. Let me go down to see the methods. Okay, the fit method, fit all transformers using this matrix X, and the transform method, transform X separately by each transformer and concatenate the results. Okay, soon we will see this practically. Let me move a bit up. And show you a convenience function, this make underscore column underscore transformer. It is a shorthand of the column transformer constructor, which actually does not require or permit naming of the transformer. Do read its documentation at your own time, and let me fall back to the Jupyter notebook. Excuse me. Fine. Let me load the same dataset that we have used in example 1. This gender column need to be one hot encoded. The IQ column is ordinal, so we will use ordinal encoder. Finally, this CGPA column has missing values under it, so we will impute them using the simple imputer. But this time we will do it in a more elegant way, and that is using a column transformer. So here is the code for the train test split already discussed above. Let's execute and move ahead. Okay. My dear friends, instead of creating the three required transformer instances and then calling fit and transform on them separately to get the three numpy arrays which we need to concatenate later on or assign to appropriate columns of the data frame, we'll make use of the column transformer class. And for this, we need to import the column transformer class from the compose module of Sklearn. And of course, we also need to import the simple imputer, one hot encoder, and ordinal encoder. To create an instance of column transformer class, I'm calling its constructor and passing it the two arguments, a list of transformers, and remainder is equal to pass through. Note that the transformer argument is actually a list of tuples. So this is the first tuple. So this transformers argument is a list of three valued tuples, and we are right now applying three transformations. This first value of the first tuple shows that the name of the transformation, and that is TFM1. You can give any name to it. The second value is the instance of the one hot encoder. And the third value is the list containing column names or maybe indices on which this transformation is to be applied. Similarly, this second tuple tells us to apply a simple imputer on the CGPA column, and this third tuple tells us to apply ordinal encoder on this IQ column. Well, this remainder is equal to pass through. This argument tells to also return any column other than gender, CGPA, and IQ as such. Although we do not have any other column, but if there was a column in the input feature dataset, it would have been returned as such. Actually, by default, a column transformer returns only the columns on which it has performed a transformation. I hope the code is clear. So let's execute this. So we have got an instance of the column transformer. And in this code cell, I am calling the fit method of column transformer by passing it the xtrain. Let's execute. So we have got a trained instance now. Let's call the transform on both xtrain and xtest. And this will of course return two numpy arrays after performing the transformations. Let me execute it. You can see the 20 rows of xtest with three input features. They have been transformed to a numpy array. The gender and the IQ columns have been encoded appropriately. And the missing values under the CGPA column have been imputed with the mean, and that is 2.8, I think, 2.88, yes, over here. I hope this makes sense. My dear students, you see the power of column transformer, which allows us to specify different transformations per column, making pre-processing a lot less tedious. And soon I will show you as to how we can use a column transformer in a machine learning pipeline as well. And for the time being, our data is ready to be fed to the machine learning model. So let's instantiate, create an instance of the linear regression model and call fit by passing the pre-processed input data. Remember, I have passed it ARR underscore xtrain, ARR underscore xtrain, the pre-processed data. Now we have our instance, trained instance. We can call predict And this is what we did in example 1 as well. That is predicting the salary of a male having CGPA of 3.5 and high IQ. And after transforming this new input manually, let me just execute it. So we have got the same output, that is 73.127 thousand rupees. So far, so good. Well, my dear friends, let me move up a bit and tell you the limitation of column transformer. The major limitation is you cannot apply multiple transforms to a single column. For example, if you see over here, we have applied simple imputer on the CGPA column. Now we cannot apply standard scalar, let's suppose, on CGPA column. Similarly, suppose this gender column has a missing values under it. So we cannot apply simple imputer and one hot encoder on this gender column using column transformer. My dear students, I think I have set the stage right, and now we are ready to learn as to how to design and code machine learning pipelines. Let me just move ahead. We have discussed the limitation, and now we are moving on to the machine learning pipeline. Okay. Well, my dear friends, let me start by giving an overview of a machine learning pipeline by using the three famous questions: what, why, and how. Simply speaking, in real world, a pipeline is a mechanism that chains together multiple steps so that the output of each step is used as input to the next step. In context to machine learning, a pipeline is a series of steps that you follow while working on your project. This could include things like acquiring and pre-processing your data, training, hypertuning and validating models, and finally deploying them to make predictions. In today's session, we will mainly be doing different types of data pre-processing in our machine learning pipeline. So our pipeline will have a lot of transformers as shown in this image. The sequence of transformers does matter as they will be called one after the other. The output of this transformer 1 will become the input of transformer 2 and so on. And finally, we will have an estimator at the very end. So this is what a pipeline is. Well, these transformers can be built in scikit-learn transformer classes like simple imputer, one hot, ordinal, or standard scalar. For outliers, if you don't find a transformer, my dear students, you can write your own transformer class by inheriting it from I think the base estimator and transformer mix-in classes, and later you can override the fit and the transform method. Anyways, let's avoid the details for writing your own customized transformer for the time being and keep things simple by just using the built-in scikit-learn transformers. Okay, so after having a lot of transformers, finally at the very end of the pipeline we have an estimator, which can be a linear regressor, support vector regressor, or a decision tree regressor, or it can also be a classifier as well. Now the next question is, why to create a machine learning pipeline? Well, my dear friends, the advantages of a machine learning pipeline are manifold, like reusability of components, ease of implementation, and expansion. But for the time being, let me describe a very basic advantage, and that will be very clear after you have deployed your machine learning model on a server and have created a suppose web interface for its end users. Once a user enters the data, you have to perform all the pre-processing tasks on it before feeding the data to the model. On the contrary, if you have implemented a pipeline, you don't have actually to repeat the code on the server. So this is the advantage of using pipeline that we are going to see today and in the next session as well. The next session in which we will learn how to deploy a machine learning model using an application. Now the next $100 question is how to create a machine learning pipeline. And let me click this link to go to Sklearn documentation page of pipeline. So we can use the pipeline method that will create a pipeline of transformers with our final estimator. The only parameter of our interest right now is this steps, which is passed a list of 2 valued tuples. In case of column transformers, we pass 3 valued tuples. Over here, we pass 2 valued tuples containing a unique name and a transformer class instance. And of course, the last transformer must be an estimator. Let me go down and see the methods. Okay, my difference we call fit to train the pipeline. This will internally call the fit method on all the transformers in sequence, one after the other, and finally fit the transformed data using the final estimator. After fit, we can call the predict method, and this will internally call the transform methods on all the transformers in sequence. The transformed data is finally passed to the final estimator that calls the predict method. Okay, we will soon see this practically. Let me move up and let's talk about this make underscore pipeline method. Like column transformer has make underscore column transformer, the pipeline has make underscore pipeline method. This is also a convenience function, make underscore pipeline, and this do not require naming of the transformers. Do read its documentation at your own time, and let me fall back to the notebook. Okay. Well, my dear students, we will implement pipeline using 2 or 3 different datasets for a crystal clear understanding. Let me load this one, and this one is my favorite, the advertising dataset. I have intentionally placed a few NANDs under the TV, radio as well as the newspaper column, which are also visible over here. So this is the advertising dataset, all time famous, having 3 input features, TV, radio and newspaper, containing the amount in thousands of rupees spent on the advertisement. And this is the sales in thousands of units. Okay, anyway. Let's check out this count of these null values. df dot is null. And let me call the sum method on this. Good. So here is, we have 4 missing values under the TV, 10 missing values under the radio column, and 2 missing values under the newspaper column. So here is the image of the pipeline that I want to create. Having 2 transformers and an estimator. Unlike column transformer, which applies a transformer on one or more specified columns and returns the resulting array, inside this pipeline, this simple imputer will be applied to all the columns, all the three columns of this dataset. And the results will be fed to the next component, and that is standard scaler, which will scale all the 3 columns, and the result will be passed to the linear regression model, which is our estimator. Let's do this practically, and let me first do the train test split. So this I think code makes sense. Okay, my dear friends, let me create this pipeline now, this pipeline object, and for that I need to import the pipeline constructor from pipeline module of Sklearn. I'm also importing the 2 transformers, simple imputer and standard scaler, as well as the estimator, that is the linear regression. Well, to create the instance of the pipeline class, I am calling its constructor and passing it the only required argument, that is steps, which is a list of 2 valued tuples. 2 valued tuples. This is the first tuple. Do note that unlike column transformer, we do not have the 3rd value in the tuple, which is the list of columns on which the transformation is to be applied. Over here, this simple imputer will be applied on the entire dataset, this standard scaler as well, and finally this linear regression. So this pipeline has 3 steps: simple imputer, standard scaler, and linear regression model. Great. Let me execute. So we have got an instance of the pipeline object having of course two transformers and one estimator. Great job done. My dear students, let me show you how to display this pipeline in a diagrammatic form. And for that, I need to uh, import setConfig method from Sklearn. From Sklearn, import set_config. So this is the method I need to import, and then I need to call it. And it has an argument display, and let me set it to diagram. You can also set it to text, which is the default value. So let me execute this, and let me now write down pipe again. So it has not worked. Diagram set config. Okay, I've placed a double equals to sign. Sorry for that. Great. Well, so this is a great visual representation. You can check out. This is the simple imputer. This is the standard scaler. This is the linear regression, and this is the actual code of the pipeline. A good visual representation. Great. Let me just collapse these. Well, now to train the pipeline, we actually call the fit by passing it the X train and Y train. Remember, the X train is just the raw data. Let's execute. So now this is a pipeline having trained components. Internally fit method has been called on these two transformer as well as on this estimator. Now we can call this predict method on this trained pipeline, which will call, of course, transform methods of the two transformer in sequence, and predict method on the linear regression estimator. Let me just execute. Great. So these are all the predicted values. And let me evaluate as well. Evaluate the model by calling the score method, but this time on the pipe object. This will work, of course, only if the final estimator implements this score method, and of course this linear regression model implements this score method. Let me just execute. So a score of 0.85, R2 score seems okay. One more thing, my dear friends, you can call the methods on a specific transformer inside the pipeline. For example, let me show this to you as well. Let me say that we have the pipe object, and instead of let's say I just want to call fit transform on this SI. So this is the name, simple imputer. So let me use this name over here, SI, and on this I can call fit underscore transform. Let me pass X train to it. Great. So it has returned a numpy array. You can see this numpy array. After imputing the missing values under all the three columns, the missing values have been imputed. Note that this SI actually, this SI is the name that we gave to this transformer while creating the pipeline. This is the name that we gave it. Okay, so let me call on SS this time. So this SS is actually this standard scaler. So let me execute. Great. This has returned once again a numpy array having three columns. After scaling all the values of the three columns, do note the NANs, as this has simply run the standard scalar transformer and not the simple imputer. I hope this makes sense. Let me move ahead. Okay, now let us do the prediction using this pipeline. And suppose we have deployed this pipeline somehow, and our user has given this input via web interface. So the user wants to predict the sales of items if the company spends 60,000 rupees on TV advertisements and 40,000 rupees on newspaper advertisements. And let's say unintentionally the input field for radio advertisement has gone blank. So we have a NaN over there. Do note that the predict method of estimator expect a 2D array. So I have created a 2D array of size 1 by 3. Note the double brackets. Let me just execute this. So we have the input. Let's pass this input to the predict method of the pipe. So this is the output. So the data has to be fed to the machine learning model after this proper pre-processing. Great job done. So if you spend this much money on the advertisement, the sale of the items will be 10.029 thousands. Great. Okay, so my dear friends, let me give you a very comprehensive example now. Uh, well, over here, if I talk about this pipeline, uh, this image shows how we designed our pipeline in this example, example 3. And in this pipeline, we had two transformers, a simple imputer and standard scaler. And they both were applied on the entire dataset. The entire dataset, all the three columns were given as input to this simple imputer. And the output of the simple imputers are again three columns which are given to this standard scaler. And that all the three columns were given to the linear regression model, which has predicted the sales of the items. My dear students, what if our dataset has numeric as well as categorical features? And we want to apply different transformers to numeric columns and different transformers to categorical columns. And for this, we of course need to use the column transformer inside a pipeline object. So this is what this fourth example is all about. Let me just load this dataset for which I want to apply this comparatively advanced pipeline. So this is the tips dataset that comes bundled with Cbone library, and you can load it using the Cbone's load dataset method. But right now, I'm loading a bit modified version of this dataset where I have just introduced a few NaN values, which you can see over here. So this dataset contains 244 rows and 7 columns. Every row contains 7 pieces of information associated with a paid account in our restaurant. This total bill column contains amount paid in dollars. The sex, smoker, day, and time are categorical columns. This size is a numeric column showing the total number of persons on that table, sitting on the table. And finally, this tip is the amount of tip paid. So this seems to be a regression problem. Given the total bill, sex, smoker, day, time, and size, we need to predict this tip. My dear friends, let me wait for the azan. After azan, I will continue. You can. Sallallahu. La hawla wa la quwwata illa billah. La hawla wa la quwwata illa billah. La hawla wa la quwwata. La hawla wa la Allah Akbar. La ilaha illallah. Okay, so I'm back. Well, so this is the tips dataset. I have just described it. My difference, I'm not going into the details of checking out if the assumptions for linear regression hold in this dataset or not. As right now, I am more interested to learn how to create a pipeline. Anyway, let's first check out the data types. Let me say df.dtypes. Okay. So out of the 6 input features, we have 4 categorical columns and 2 numeric columns. Great. We need to encode the categorical features to make them ready to be fed to the machine learning model. Let's check the unique values under the day column. Let me say df.day.unique. So Sunday, Saturday, Thursday, and Friday. So we have 4 unique values under the day column, and when we will apply one hot encoder on this, we will get 4 binary columns, or maybe 3 if we drop the first to avoid multi-collinearity. Similarly, you can check out the rest of the columns as well. Let me now check the missing values under different columns. df.isNA. Let me call sum on it. So you see the output label tip has a missing value of 1, and in the input features, the categorical column, this sex and smoker, have missing values which can be imputed using the most frequent strategy. Similarly, this total bill is a numeric column, so we will prefer using mean strategy to impute the missing values under this column. Well, my dear students, it is a normal practice to drop all the rows for which the output label has a missing value. So instead of imputing the output, we just prefer dropping that row. So I think I have done that, yes. For this, you can use the drop NA method of data frame. Since we want to drop the rows, so this axis is equal to 0. And this how is equal to any means drop the row if any one of the values is missing. Well, this subset argument specifies the column to be considered. So in summary, I can say that this method will drop all the rows of the data frame DF where the tip column has a missing value. And of course, the in place is true, so this will happen in place. Let me execute. You can see we do not have any missing value under the tips column anymore. And let me check the shape of the data frame as well. df.shape 243. So only one row is dropped. Previously there were 244 rows, so there was only one missing value under the tips column, and that row is dropped. So now we have 243 rows. Great job done. Well, my dear friends, before doing any transformations, let's do a train test split on the input feature matrix X and the output array Y. Let me just execute this. Remember, the training and the test set has missing values under the total bill, sex, and smoker column. We could fill every value in these columns before splitting, but this would result in using that information from the test set to fill the training set. So remember to split before doing the transformation. So this will avoid information leakage. I hope this makes sense. Let's design the pipeline now. Just take a deep breath with me. Let's see the X train. So this is the X train. Total bill, sex, smoker, day, times size. Fine. Okay. So we have these 6 input features, and we want to build a pipeline having linear regression estimator at the end to predict the tip. And this is the image in which I have designed this pipeline. And suppose this blue box is our trained pipeline, this blue box, bigger blue box. The input to this model are the 6 input features values, and the output is the tip shown at the bottom over here. Now, before I show you the code to create this pipeline, let me describe it using this image properly. Well, my dear students, these two boxes shown in dotted green lines are actually two pipeline objects. This left one is named as categorical transformer, having a simple imputer and one hot encoder. This right one is named as numeric transformer, having just a simple imputer. My dear students, remember this right simple imputer will use mean as the strategy as it is going to impute the numeric data. On the contrary, this left simple imputer will use most frequent as the strategy because it is going to impute the categorical data. Well, after creating these two pipelines, I will join or combine them using a column transformer, which is shown as this red dotted box. So in this red dotted box, I have joined these two pipelines using a column transformer and I have named it preprocessor. Well, then I will create another final pipe shown in this blue box containing this preprocessor, that is the column transformer having two pipelines, a standard scaler, and an estimator, which is a linear regressor in our case. I have named this final pipeline as model. Once this pipeline object will be created, I will call fit on it, which will internally call fit on all these transformers and this estimator at the end. After we have the trained pipeline object, we could call predict. Let's suppose again a user gives these 6 values as input to our pipeline object. The two numeric values, that is the total bill of 100 and a size of 4, will go to the preprocessor, and being numeric values will go to this numeric simple imputer. If any of these two values are nan, they will be imputed. The remaining 4 categorical values, that is sex, smoker, day and time, that is this mail, yes, Sunday and dinner, will go to the preprocessor, and being categorical variables, after imputation they will be encoded using this one hot encoder. And the output of this preprocessor, this overall preprocessor, which is a column transformer having these two pipelines, will be sent to this standard scalar transformer, whose output will be sent to this estimator, and which will predict the tip, which comes out to be 10.34 in this case. Now let's do this practically. This code cell is actually creating the two pipeline objects named categorical transformer and numeric transformer. If we move up, we see in this image, we are actually creating these two pipelines shown in green boxes over here. This categorical transformer having two transformers, simple imputer and one hot encoder, and this numeric transformer having just a simple imputer. I think we have already discussed the syntax to create a pipeline object using the pipeline method. And to its steps argument, we need to pass a list of two valued tuples, the name and the instance of the transformer. Well, let me highlight this. This highlighted code is the categorical transformer having a simple imputer with strategy most frequent and one hot encoder. And this highlighted code is creating a pipeline with the name of numeric transformer having just a simple imputer with a strategy of mean. Let me just execute it. Great. We have now two pipelines, and of course they are untrained. Let me move up. So we have successfully created these two pipelines shown in green dotted boxes. Now it's time to combine them using a column transformer. We need to combine them using a column transformer. Let's move down. And it is done over here. We have already discussed the syntax to create a column transformer. To its transformers argument, we need to pass a list of 3 valued tuples. The name of the transformer categorical, and then we have the transformer to use. Over here I'm using a pipeline, and that is categorical transformer, and then a list of column indices or names on which we want to apply this transformer. So these 1, 2, 3, 4 are the column indices of the categorical columns, while this 0 and 5 are the column indices of the numeric columns. Let me just execute it. Great. Let's move up again. So my dear students, we have successfully combined these two pipelines using column transformer and have named it preprocessor, shown with this box with a red dotted line. Now we just need to create a final pipeline object in which we have this transformer, standard scaler, and estimator. And we will name this final pipeline object as model. Once created, we will train it on xtrain and will evaluate it on xtest. Let's see the code to do all of this task. Okay, so here is the code that creates a final pipeline named model, having just 3 steps. You see, this is the first step, which is the preprocessor. Then we have the second step, that is the standard scaler, and the third step, which is the estimator, which in our case is a linear regression model. Let me just execute this. Great. Now this is of course the visual representation of our pipeline model. You can play with these arrows. You can open this. So this is linear regression. This is standard scaler. So we have one hot encoder. This is the code for one hot encoder. It's code for simple imputer. So you can open up all these. So this will just let you know what all is being done in this pipeline. Great job done. Great. Okay, so pause this video, my dear friends, for a minute or so and map what all we have done so far with this visual representation of this pipeline. And let me move ahead. And now it's time to train this pipeline by calling the fit method on it and passing the xtrain and ytrain. Remember, when you call fit on a pipeline object, this model is a pipeline object in this case now. Internally, a fit transform is called on all the transformers and a fit on the estimator. Let's execute. So this is now a trained pipeline. Well, to evaluate, we can call the score method and passing it the xtest and ytest. And once again, remember, when you call the score or even the predict on a pipeline object, only the transform method is called on transformers and predict on the estimator. Let me execute. Great. So this is not a very good score. Anyways, let me now give a simple input to this pipeline model with a total bill of $100. Sex is male, smoker is yes, day is Sunday, time is dinner, and size is 4. Let's pass this test input to the predict method of our pipeline model. Let's check this out. Great. My dear friends, you see the beauty of using pipeline? We don't just have to change this. This has been automatically pre-processed once we pass this to the pipelined model. Great. Well, my dear friends, the way we have used the cross validation with machine learning models, we can do the same with pipeline models. You see this code where I'm just passing the pipeline object to the cross val score. Remember, this model is the pipeline model. I'm passing it the cross val score method. The rest arguments are same as discussed in previous sessions. They are x train, y train, a cross validation value of 5. That means use 5-fold cross validation. And finally, this scoring metric is R2, which is the default for linear regression. Let me just execute. So these are the 5 R2 scores for the 5 different splits. And of course, we can calculate the mean of all these 5 R2 scores by calling mean on it. Great job done. Well, this 0.413 is not all that a good R2 score, but I think it's good job done. I have tried my best to make you understand all the nitty-gritties involved in designing and coding scikit-learn pipelines. Well, my dear friends, over here I have placed all the code in one cell. You can see this. All the imports. Then I have read the data and doing our train test split. And this is the code for creating the entire pipeline. The entire pipeline is being created over here in this code cell. And finally, after fitting the pipeline, I'm printing the R2 score using cross-val score method and predicting a test input as well. Let me just execute. This is the same code which we have discussed. Great job done. Okay. My dear students, here is a task for you to do. This is a big mart sales dataset having information about different items across, I think, 10 stores in different cities. The aim is to build a predictive model and predict the sales of each product at a particular outlet. So these are the sales. Please do a detailed analysis of this dataset and finally create a pipelined model as done in today's session for this dataset. And I think we have also studied grid search CV in the previous session for hyperparameter tuning, finding out the optimized hyperparameters from grid. And please do try to find out the best hyperparameters of whatever regression model you are using for this. I think you will be able to do that. My dear student, that is all for today's session. I hope today's session was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. I wish you all the best, happy learning, and Allah Hafiz.